All right, let's get started. As you know, y'all have an exam today. So, what? I'm just kidding. This isn't the exam. It's just a pile of papers I found on here. That's right. I'm just messing with you guys. We have a review today. I promised you a review. So you're gonna get a review. Thursday. What? The exam is this Thursday. We all ready for that? Okay, well, we're gonna change that today, aren't we? Yeah, you're not ready, and we're gonna change that today. You're gonna be ready, right? No, the review session is to make you less scared of the exam. It's so you know what's going to be on it. Okay, so here's the deal. The exam we're going to have on Thursday is worth 200 points. Okay. There's going to be 10 questions on it. And so I'm going to give you a breakdown, question by question, on what you need to study for the exam. Except for the first two, because those are freebies. If you've been showing up to class with a pulse, you'll get the first two. So we're going to start on question 3. Are there any questions you have for me before we start the exam review? None about project 2. So we're all good there.
Until we start, we can't be like, we've been stuck in between when we started. So we may have like questions about project 2 when we start the project.
Oh, okay. Most people haven't started it. That's fine.
Waiting for my project 1 to better. So when do we want to have a row for, so like if 17 is a component of a row? Do we want to have some row where the vertex 17 has the component label 17, or can we just assume that if it's a component label, it's included in the other ones that are listed?
No, because the component ID needs to be arbitrary.
Well, I just take the like small state of eight.
You can do that if you want to, but that's not part of the spec. So you still need to include the source, the original source. So you're going to have one row in there. If you use the smallest page ID, you're going to include one row in there, 1717. Anything else? All right, let's start the exam review. Okay. I don't have anything prepped, so I'm just going to look at the exam as we do the review. Okay. So the third question on this exam is going to ask you, and also the first 3 questions. The first 3 questions are going to ask you about the process that you use to start a Spark cluster and use a Spark cluster. So make sure you are familiar with the ins and outs of the step that you use to both start an interactive EMR cluster and start an EMR step. Make sure you're familiar with all those. Make sure you know how they work. Make sure you know the commands and what everything means. And so I believe we went over that a couple of weeks ago. We went over in detail the SSH command and what everything in there means. And then the next day after that, we went into CIDR blocks and stuff, which will not be on this exam. It'll be on the next one. So for questions 1, 2, and 3, make sure you understand the setup process. So if you understand that process, and the first 3 questions are freebies. Do you have any comments on that? Okay. I'm gonna put this into an announcement for the exam on Canvas. Ready for class. Okay. So for question number four is going to be about the Wikipedia dataset. Make sure you, and this is again, if you did the project and you did the project correctly and you understood Wikipedia's data model, you should be able to answer this question. So make sure you understand Wikipedia's data model, what all the different tables from Wikipedia you used are. Make sure you know what all the columns mean and how they relate to each other. Okay. Number five, make sure you understand. Yeah,
Yeah, and this you will not include the article one, just making sure.
no, we didn't use the articles for the project, so I'm not going to test you on it. Anything else?
Hmm.
Okay. For number five, make sure that you understand Amazon's EC2 service. Make sure you understand all the instance types and the resources that are available to it. Make sure you understand the difference between all the different EC2 instance types. That's really important. That includes sizes and families. Do you want more detail on that? Okay. Whoa. All right. We look at this list of Amazon EC2 instance types, and we can see, different families of instance type. We can see general purpose instances, compute optimized instances, memory optimized instances, and so forth. So what you need to do is you need to know the types of resources that are available for these instance types and what what the different sizes mean, how it's connected to the amount of resources they have, and what the different abbreviations mean. So general purpose instances are prefixed with the letter M. So anything starting with M is a general purpose instance. And general purpose instances have certain properties. They have, at least N-type instances, have a defined ratio of virtual CPUs to memory in gigabytes. They have a certain amount of network bandwidth. They can also come in AMD, EPYC processor flavors, Graviton flavors, or Intel Xeon or Cascade Lake processors. So by looking at the instance family, you need to know the difference between these things. So for example, the M6G instance types uses Graviton processors. And so these are ARM processors, which are different from Intel and AMD processors, which use the x86 architecture. And this difference is important when you're building an AWS cluster. Because a lot of the time, um, maybe Intel or AMD chips may have specialized instructions for you to use that aren't available on ARM, but ARM tends to be cheaper.
Okay, are these type of processors true for the whole family? They're all of the M's? use this type of processor?
No, only if the type of processor has kind of a G suffix, that's for graviton. So it uses graviton processors. If you look at M7A, M7A uses AMD EPYC. And if you look at M7G, M7G uses graviton. So M7G uses graviton, M7A uses AMD EPYC, and what's this? M5 uses Intel Xeon. So know the difference. And this pattern is common with all the instance families. So regardless of whether it's M type or C type or R type, G, A, and no other suffix refers to the fact that this instance family has a graviton processor, an AMD EPYC processor, or an Intel, respectively. So if we look at memory optimized, we can see exactly the same pattern, right? We have R7G, which is a graviton type processor, but in an R type instance, this is memory optimized. And so per CPU, we have additional memory. So an R7G has twice as much memory per CPU a as a general purpose instance does. That part makes sense? The I believe, is improved network bandwidth. So R6I is Intel Xeon. Yeah, I believe it's R6. No, that's N. I think it might refer to Ice Lake. I think the I might refer to Ice Lake. I think N refers to network bandwidth. Yep. Yeah. N is for network bandwidth. Never mind. So I might refer to Ice Lake. And then R5, it refers to Intel Xeon Platinum. Yeah. So it's just different architectures. So know what all these mean. I don't think you need to know what everything means. You need to know what the G suffix means on the instance family. You need to know what the A suffix means. You need to know what not having a suffix means. So, R5 versus R6G, that's different, right? Intel is basically the default there if there's no suffix. So you need to know that. And you need to know what the D suffix means. So you can see X2GD over here. These things are totally separate. The D is unrelated to the G here. The D refers to local disk. Local disk versus elastic block store. So you'll notice, like let's say in R5 instances, right? We have R5 instances of various sizes. So we have R5 large over here that gives us 2 cores and 16 gigs of memory. We also have R5D large, which has the same number of cores, the same amount of memory, but this has EBS only storage, and this has a 75 gigabyte local SSD. And you can say the same thing with M5. M5D have the same relationship as R5D, except with an M5D, it's 2 virtual CPUs and 8 gigabytes with the same amount of SSD storage.
For the bandwidth also?
No. So you don't need to memorize every single instance type here, but make sure you know the difference between an R type, an M type, and a C type. And make sure you know what having a G suffix means, what having a D suffix means, and what having no suffix means. That's the important part. Having no suffix. So having no suffix refers to using an Intel processor. Well, a suffix is for AMD EPYC. It's not that important. unless you're doing something pretty application specific, um, an AMD EPYC might be interchangeable with an Intel because they use the same architecture. So they should be able to even run the same compiled binary code, theoretically, assuming it doesn't use any specialized instructions or anything. But the most important one for this class is the D suffix. So when I mention instance types on the exam, look at it carefully. Make sure you know what resources it has when answering the question. That part makes sense?
Yes.
Okay. So know what those three families do. Know what the sizes mean. And the sizes really just refers to the number of CPUs. So you'll look at M5 large and that has two CPUs. If we go down, you look at R5 large, that has the same number of CPUs, but it has double the memory of an M5 large. So like an R5 large has two cores and 16 gigs of memory. An M5 large has two cores and 8 gigs of memory. So by that logic, an R5 would be more expensive because it's like an M5, but it has twice as much memory. So the sizes really just refer to the number of CPUs. And a lot of the time, the instance family will tell you what the ratio of virtual CPU is to memory. And for C-type instances have half the memory per core that an M-type does. So for like a C5 large has 4 gigs of memory and 2 cores. So know what these ratios are and know what the sizes mean. It's kind of an easy way to do it. Every time, we go up a size, we double the core count to a point, and then things get a little weird. This part makes sense. Any further questions? Margaret, you have a question? Okay. 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 Question 6. Okay. Question 6 is make sure you understand Spark's execution model. So you need to know what a Spark executor is and what a task is and how tasks are assigned to executors. You also need to know how Spark executor resources are defined. So, a resource or an executor has a certain number of cores assigned to it, a certain amount of memory that it's allowed to use, things like that. So make sure you understand Spark's execution model. Can you put any more detail there? Yeah. assigned to executors. Do we feel like we need further clarification here? Can you speak up? You will definitely need to know shuffling for this and for other questions. There's a lot of emphasis on aggregations in this exam because we spent 3 lectures on it. And because it's very important, because um, a lot of the difficulties that you will have when programming in Spark with real big data is trying to make sure your shuffles don't kill the cluster. Oops, you ran out of memory somewhere. So there's a lot of emphasis on shuffling in the exam and aggregations and how those function. Enough said here. Okay. So for question number 7, you need to understand which Spark operand or which Spark operations will actually trigger a shuffle. So in reading the Spark code, I want you to be able to tell how many shuffles something is going to do. So just by looking at the code, I need you to tell me whether or not this Spark code is going to cause a shuffle or not. Oh, do we have a question in chat? Is that what this icon means? No. Oh, that's from AWS. Okay. 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 Questions 8 and 9 are you need to understand how aggregations work. So you need to understand how the data flow for certain aggregations work. So you know how Spark, when it does an aggregation, it will kind of do a pre-aggregation, create the aggregation states, and then do the shuffle, and then we'll merge all the aggregation states to the same key. We talked about that in the aggregation lectures, right? Right? Okay. I don't know if there's more detail I should put here. I don't think so. Um, pre-shuffle, aggregation, and post shuffle. That. Okay. Has everyone looked at the SQL data frame plans for stuff?
The like flow charts while it's running.
Yeah. So those, did you have a question? Okay. So yeah, those are the DAS kind of flow charts that will tell you, you know, how the data is being handled by Spark. It'll tell you when certain joins are happening. It'll tell you when pre-aggregations happen and when an exchange happens and when a post-aggregation happens, all that. It's great. And it'll give you information on like the size of the hash tables it uses. It's pretty cool.
And that's the DAG.
That's the DAG I'm talking about that you can look at in the SQL/data frame tab in the Spark UI. That's also how I graded a lot of your projects. Is I looked at the DAG.
Can you only look at that Zoom interactive? Or work with this?
Nope, you can use it when you're running as an EMR step or interactively. It doesn't matter. So I ran all of your code as a step. So I was able to see it there too. Questions for that one? Okay. Now, the last of the 10 questions is I am going to ask you to put up an aggregation state. I'm going to give you an aggregate function, and I'm going to ask you to define the members of that interface. So I'm going to ask you to define the zero function for that class, the reduce, the merge, and the finish. Create. Okay, does that part make sense? So it'll match the exact interface of a user-defined aggregate function in Spark. And to help you out with this, I just uploaded the aggregation state code into the resources repository because I realized I forgot to do that. So it's all here. And it has two other things. It needs a buffer encoder and an output encoder. I don't care about that because that's just serialization business. We handled this stuff at a pretty high level. Next time I teach this class, it'll probably be in Scala. It'll make you do a homework that looks like this, but for now, let's just do it theoretically. And you can practice creating aggregation states by basically just putting the class into this code and defining your partitions as you see fit in your data. You okay?
No.
Why? What's going on? My hope is that the exam will be appropriately challenging.
On our laptops, is this actually coding or are we?
Paper.
It's paper, true.
So I'm not going to grade you on your syntax. As long as I can understand what you're doing, then we're good. Just don't code in English sentences. or any other natural language for that matter. For those of you looking for loopholes. And if you write the code in Lisp, I will be unhappy, but I'll deal with it.
Like paying in pennies.
Exactly. Okay. Oh, I forgot to put point values here. So I'll tell you how many points each one is worth. These are 10 points each. Have to actually look at the exam to remember what points I assigned.
I have a question regarding the understand Wikipedia data model. You asking from the what we have done in the mutual pair. I mean, project one, like how we have connected the left, some inner joint or left joint, and what was the data column needs and all that.
Yeah.
These things.
I mean, if you all did the project, so I don't really expect you would need to study for that anyway.
Yeah.
So I'm hoping that since they're all short answer, not all choice specific, it will there be partial credit?
Yeah.
Okay.
Yeah, this isn't going to be like your, what was that? Physics 211, where you get one step wrong and you get the entire question wrong because the class has 150 students and the professors can't go through every page. I have 13 students. I will read your exam.
How long the answers are we expected to be? Until it makes sense to you.
Yeah.
It's not.
The amount of space I provide for you on the exam paper is not indicative of how much I expect you to write.
The answer should be like,
I'm,
if it explains the questions that much you want, right?
I mean, be detailed
Yeah.
be detailed in your answers, but you don't need to write me 7-page essay for an yes. Succinctness is best.
The exam will be for 75 minutes.
Mm-hmm. Normal class period. No, you don't get more time if you arrive early.
That's what we were practicing ourselves for the exam.
Mm-hmm. Is that why everybody showed up early? You're practicing for exam day? Or did you just know the exam was today?
Okay, so I don't see anything on here on the difference between like merge joins and the hashing domains.
I might ask that in the next exam. I didn't have enough space on this one. I won't ask you about the different types of joins or aggregations.
When we were talking about aggregations and what we create aggregation states for, we had a whole column of things that create that are aggregation functions. And then we have another column, things like median, rank. Those are not considered aggregations.
Okay, I know I said I would look into median. I didn't do that properly. So median is an aggregation function, but it's a little bit different because the size of the aggregation state for median is linear as you continue to add rows into it, right? Because you need the entire distribution in order to know what the median is. Um, for rank, that's not an aggregation function, that's a window function, which is different. So I'm not going to test you on window functions because we didn't really talk about them.
Okay, so in median, is it gonna, how does it do it? Like, does it try to put everything on, it can't put everything on one?
My guess is that that actually is what it does. At least if it's trying to calculate the exact median, um, there might be approximation algorithms that can save space and do it more efficiently. But my guess is that it will just collect all of the stuff, all of the values into an aggregation state and then sort it. But I'm just guessing. Don't quote me. Because for the median, I don't really see any other way you could do it if you're doing it by key. And if you weren't doing it by key, that might be even worse because if you wanted to take the median over the whole data set, you'd have to sort the entire data set. And I might talk about this like at the very end of the semester once we've actually finished our experiments with it. But I finally did to get to compare the training performance of training a random forest model in Spark versus training a random forest model in Scikit. The random forest model takes 2 days and the Scikit model takes 20 minutes. And the Scikit model produced was twice as large. We don't know the performance of the model yet. I haven't tested that, but the fact that it was so fast is a little bit suspicious. So I am very excited to potentially give like a bonus lecture on that at the end of the semester if we're able to test the model's performance that we trained with Scikit, because it would be a really interesting case study. It'd be like, hey, we spent the entire semester learning Spark. Did you know that it's useless? Not really. It's great for some things, and maybe not so great for others. In general, sorting the data in a distributed system is ridiculously expensive. And that's what a decision tree has to do over and over and over again, which would explain why it's slow. I went into the data science AI director's office and hey, I told him, hey, this takes 20 minutes to train. He's like, no, it doesn't. Absolutely not. Something is wrong. I was like, maybe, but I don't know. So we have like a solid half hour left, and I don't really feel like covering anything new. So we can set aside the rest of the time for questions, or if we want to answer some project two questions, like around how the iterative connected components algorithm works, we can do that too. So what do we want to do here? Do we feel satisfied with the information we've got here? Yeah.
The execution model, so the partition, the different data partitions are stored on the executable.
Yeah.
Executors can have multiple cores,
Mm-hmm.
but there's but the tasks are sent to the assigned to the cores.
Tasks are processed by a core.
Accessed by a core. Okay, so what is doing all of that allocating? You mentioned like how they're allocated. Is that what you mean? Or like, is there, I'm kind of always still been fuzzy on the whole. Like the book says is that as far as how that all are working together. So that the stage.
So you have a job, and then that describes an execution for Spark. Usually what that does is it'll take all of the previous computations that are defined as part of your DAG, and it all collapses down into one result, right? So usually a job is computing the results of a DAG. That's usually what a job is. A stage is a node in this DAG. Because if you look at the Spark DAG, you'll notice that when you look at the different stages, or when you look at the different nodes in the DAG, every stage is its own node. So the stages define the individual members of the data flow. And how it usually works, and this isn't like a perfect one-to-one correlation, but how it usually is if you have a shuffle, then the result of the exchange will start a different stage. So stages may be separated by shuffles. That's more of a general observation than a rule of thumb. But I've noticed that Spark stages tend to be separated by shuffles. And if there's no shuffles going on, it all kind of just winds up being the same stage. Do we want to look through an example Spark DAG and I'll show you what I'm talking about? Okay. This one? I think it was. Okay, I think this is the DAG that I used for project one, or this is the cluster I used for project one. One of them at least. Actually, I'm gonna what just happened? Oh, I see. I'm gonna post this on Canvas before I forget. That was a problem. That was not supposed to happen. Okay. Oh, this is taking its sweet time. Okay. But this isn't the actual job DAG. Let's look at the different stages that it's separated into. Oh, it's separated into multiple jobs. That's annoying. Okay, let's look at the first one. DAG vision. That's not helpful. How about this one? Okay, there we go. All right. Wonder if it has stage example or stage information here. Not really, but this is more helpful. Okay. Yeah. Okay. So this is the DAG I usually use to help me grade your code. And it makes it a lot easier for me to spot errors in your code because it'll tell me the number of output rows. And honestly, even though it's not that much information, the number of output rows for each member of this DAG is invaluable. Because most of the errors, or most of my programming errors when I'm writing code in Spark, is stupid stuff. And it can easily be caught by checking the number of output rows in every stage in the stack. Because it's like, oh, I joined on the wrong table, or oh, I did the wrong kind of join. I was supposed to do a left, but instead I did an inner join. Things like that. Those are the kind of issues that just looking at the row count will fix easily for you. Makes debugging so easy. And then for the actual job, I don't know why this was split into 4 jobs. Spark will do what it does, I guess, but you can see this big scary DAG here. And you'll notice that all of these tend to be separated by an exchange. An exchange is a shuffle. Because you can see the exchange here, and it's received as a shuffle read. And you've also noticed that the larger you make your cluster, if you make a bigger cluster, it will process your data faster. Right? And there are 2 reasons for that. One is because there's more memory for your cluster to work with, so it doesn't have to store as much data, if any, on disk. And there's also just more processors. More processors means you have more stuff that can run in parallel. And an executor can have multiple processors associated with it. So if you look at the executors tab, we'll see I will use processor, CPU, and core interchangeably, by the way. So if an executor has 8 cores, then that means it's capable of running 8 tasks in parallel at the same time. And if you look at, the number of tasks that are currently running, that's what you'll see.
Okay, when we set up our instances, we have a driver, and then we have the nodes that are actually doing it. Are there multiple executors on each of those? Or is that?
There can be, it depends on your configuration. You can have multiple executors per node if you want to. I usually don't. I usually prefer not to. Just keep it simple. Have 1 executor per node. Sometimes it helps to separate things out though, because if you have a process that gets too large, that there might be, some shared resources in that process that multiple threads have to access at the same time, and that just slows everything down. So sometimes it's best to limit the size of your executors to limit the amount of scheduling and contention overhead between the threads. That's actually what's it called? Has anybody ever heard of Beam? It's the virtual machine that Erlang runs on. Has anyone heard of Erlang? Has anyone heard of Ericsson?
1 for free.
Okay, like Ericsson is this giant telecommunications company from Sweden. They actually bought Cradlepoint down the street a while ago. And they invented Erlang and the Erlang virtual machine Beam so that they could write, reliable distributed systems. So that even if it crashes, it'll just restart itself automatically. And the cool thing about the Erlang virtual machine is that between the threads, none of the data is shared. So if you want to transfer information between threads in the same process, you actually have to copy the data, which is really cool because it means that Erlang's VM can perform garbage collection in a totally different way than practically everything else does. Because in order for garbage collection to work, you have to basically stop every thread in the process from running, because every thread can access the memory space. Every thread can change the memory space. So you have to stop all the threads before you clean up the garbage. But Erlang is really cool because in order to garbage collect, you only have to stop 1 thread at a time. Anyway, So do you understand this part? Is that you can have you cannot have the same executor shared among multiple nodes. An executor runs on exactly one node. A node can have more than one executor. But you cannot have an executor run on more than one node because an executor is a process. This process has to be governed by an operating system, and an operating system doesn't run on multiple machines. It just doesn't. When you have multiple machines, you're communicating between different running instances, perhaps of the same operating system, but different running instances of the operating system. And network communication is abstract, which is interesting because even though your machines are all communicating with each other, because they all follow the same protocol, unless they're explicitly told, they have no idea they're communicating with another machine that's the same operating system they are. So theoretically, you can have in your Spark cluster, you can have a mix of Mac, Linux, and Windows machines all running in the same cluster, and they won't know the difference, theoretically. In practice, that would be a huge pain, but theoretically. Any other questions about the Spark execution environment deal? Any other questions about the exam?
So eighth and ninth question is related to this one, right?
Well, not exactly. Questions 8 and 9 are more theoretical. In the sense that like we have aggregation, the data flow during aggregations, and they work in a specific way. Why do they work that way? Got to go all the way down. Shuffled hash join. Shuffled hash join into a hash aggregate. And then this is all the way down. Oh, so you'll notice. So we have a shuffled hash join, and yeah. You'll notice that we have the pre-shuffle aggregate and the post-shuffle aggregate, right? So what this looks like, okay, see this label here? It's doing a partial max. You see that?
Yes.
Yeah, so it's doing the partial max. This is the pre-shuffle aggregate. That's that right there. And so then it'll do the exchange. This is the shuffle. Then after the exchange, it'll do the complete hash aggregate. So you can see the two parts to it kind of work together. There's the pre-shuffle aggregate, and then there's a shuffle, and then there's the post-shuffle aggregate. Now I'm going to ask you a question. What's the difference between the pre-shuffle aggregate and the post-shuffle aggregate? They aggregate in different ways. What's the pre-shuffle aggregate doing?
What you were talking about the execution, that is related to sixth question, right?
I mean, sort of. This DAG is connected to basically everything you do in Spark. This is Spark's execution model. So if you understand this, you'll understand everything that Spark is doing more deeply. So who can tell me? We have this pre-shuffle aggregate. We have this post-shuffle aggregate. What are they doing differently? There's something fundamentally different about the nature of the first aggregation versus the nature of the second. So what are they doing differently? Okay, let's go over the first aggregation. What does the first aggregation do? It creates the aggregation states. Okay, what else does it do? Huh?
Refers to the previous column.
The previous column? I'm not sure what you mean.
Refers to the column whichever the data set is focused on.
Yeah. So, we're taking the max, that's our aggregation key, or that's our aggregation function. And what it will do is it'll create the aggregation states, and for every value of that column within the aggregation key, it will add that value into the aggregation state. So after the first stage, what you're left with, or after the first aggregation, what you're left with is a bunch of aggregation keys plus the states for those keys, right? And that's on the already existing partitions, because we're not repartitioning before we do the first aggregate. Then we repartition, we do the shuffle, we do the exchange, we make sure everything with the same key goes to the same machine. When we receive all of these rows on the other side, they consist of the aggregation key and the aggregation state. They're not individual rows anymore. So the second aggregation merges different aggregation states together. The first aggregation creates the aggregation states and adds all of the rows to the aggregation. Does that difference make sense? Because by the time we get to the second aggregation, all the aggregation states for all the keys have already been created.
Everything else are the merge functions. So you said they were the four methods, you have so when you create it, you do that zero value method, and then you do the reduce method.
Yes.
Merge functions until you get to the end and you finish.
Exactly. So this first aggregation, it calls the zero method on the aggregation state class to create the initial value, right? And then during the first aggregation phase, before the shuffle, it'll call the reduce function and add all the rows to the aggregation state for every key, right? Right. All right. Then it does the shuffle. And then after it does the shuffle, it will take all the aggregation states under the same key, and it will continuously call the merge function until we only have one aggregation state remaining. Then after we only have one aggregation state remaining, it'll call the finish method on the aggregation state to produce the final value. Does that part make sense? Do we want to look through the aggregation state code? Like the examples? Okay. So let's look at this average, right? This init is the equivalent to 0. You can call it init if you want in the exam. I don't care. So this init is the equivalent to 0, to the 0 function. And this creates your first initial value. The reduce is when you add a new row, right? And when you add a new row, you need to increment the total value by the value of the row you just added. You need to increment the count by 1, which is the number of rows you added to this aggregation state. Merge is when you take two aggregation states and you combine them into one. So the only thing we have to do is add the totals of the two together and then add the counts of the two together, and then bam, you have a merged aggregation state. And then for the finish is when you take the final aggregation state for every key and you actually turn it into the value that the aggregation function is supposed to return. So the return value for the average aggregation isn't supposed to be two numbers, it's supposed to be one, which is the average. So you take your aggregation state and you do whatever transformation you need to do to turn it into the thing you're actually looking for. All that makes sense. Great.
Okay, so if you are aggregating by key, once you've created your aggregation state and running those first two methods in doing so, then you shuffle based on the key. So that then all of those things are together. So then it does all of the merges until it has only one aggregation state per key. And then it can do the finish. So when you're aggregating by key, you only have one set of shuffles you have to do.
Mm-hmm.
Okay, but if you're not aggregating by key, do you do more shuffles?
No.
Okay.
Because when you don't aggregate by key and it's a global aggregation, there's only one aggregation state at the end, right? And that's the single global aggregation state. So what Spark will do is there probably like isn't even a shuffle at all. There might not even be a shuffle because the data doesn't need to move anymore, right? Because every single partition can just get collapsed into a single aggregation state. And we have way fewer partitions than we do rows in Spark, really. So, let's say we're working with 32 partitions in our Wikipedia data example. We're working with 32 partitions. And so if we're working with 32 partitions in the initial phase before we do the final merging of the aggregation states, that means we have 32 aggregation states, one per partition. Because you just go through every single row within the partition and add it to the same aggregation state. And so then you can just send all 32 aggregation states to the driver, and then I wouldn't call it a shuffle. You're only sending 32 rows. You're not really, it might be like technically a shuffle because you're like, sending data over the network and whatever, but not nearly to the same scale as an aggregation by key. Because in an aggregation by key, you might be dealing with millions of different unique values that you all have to have the aggregation states for, right? But here you only have one aggregation state that you care about at the end of the day. And, the driver node isn't really supposed to do anything, but you can send 30 values to the driver node. Like if you can't send 30 values to the driver node, then it's a useless piece of crap. Doesn't have any resources. So when I'm thinking about it, a global aggregation might not even require a shuffle, but we should actually just check the Spark tag to make sure it's not shuffling. But my guess would be no. Why bother shuffling if you're only sending 30 rows over the wire? That sounds like work, which we don't like because we're computer scientists. Do we have further questions on the aggregation states? We have questions about other stuff. Are we all stoked? Yes.
So in seventh, you could provide the code and ask that which operation something. In seven?
I'm not going to tell you exactly what the question is. You just need to know which operations trigger a shuffle. How are we doing? Do we feel better?
Yes,
Good.
but still not prepared for shelter, but no other options.
I mean, if we don't want to use the next 10 minutes, I'll take the time back, but I can just sit here for 10 minutes until somebody thinks of something to ask me. This is your time.
I have a question about this.
Mhm.
When we read and write to like truncate or like the checkpoints
Okay.
project,
Yeah.
is that all we have to do? Just write and then read back?
Yeah. Spark also has like a checkpoint function specifically for this purpose, but I found that it doesn't work as well for whatever reason. I haven't figured out why. Maybe I'm doing something wrong. At first, I thought it was because you have to manually set the checkpoint directory in Spark. At first, I thought it was because the local disk SSDs are mounted to a particular path on your EMR nodes. And so I thought I was mounting to the wrong path. I switched it to mount to the right path, and it still didn't work. So I'm not really sure what happened, but I have figured out that just doing it to and from S3 worked really well. So that's what I started doing. And going to and from S3 is fast anyway. But yeah, you can use checkpoint if you want, if you can get it to work. And maybe it will work this time around because what I noticed is that using the Spark checkpoint method worked for smaller data set sizes. And then I tried to because I've done connected components like at work, um, for a specific business purpose. And we had an automated uh it's part of our identity pipeline. And we used a kind of Spark graph library that will do connected components for us, and it does the checkpointing. But the problem is we made a change to how we did our pipeline, and we tripled the data going into connected components. And then it broke. And I'm not sure why. So I basically wrote a connected components algorithm myself in Spark, and then I did it with the reading and writing to and from S3, and that worked. I don't know why. I don't know why checkpointing didn't work. It should have, but I'm not sure. Oh, also, side note, this was all of you probably already know this already, and I will amend the project 2 spec, but you are not allowed to use anything like GraphX or graph frames in this project. So these are libraries that have predefined connected components methods for you. So you're not allowed to use those in project 2, which I think is rather obvious, but I think it needs to be said. So don't use those. When you go to work somewhere in the future, you can use those, but this is like 321 in the sense that we're implementing it ourselves so that we know how it works. And then you never have to do it again, I promise. Unless you take another Spark class somewhere that also forces you to do this, but I can't control that. So I will amend the project 2 spec to be explicit about that because it is not right now, but I don't think that was part of any of your plans anyway. That was just a quick side note. Other things? No other things? We're satisfied with all the things? No?
No.
Far from it.
Well, what are the things that we still need to talk about? We have 5 minutes, go. And we also have office hours right after this. Help me out here, guys.
What we covered of how this works, the aggregation sync work. How the whole process works. That's specifically how it works when we're doing a hash aggregation, right?
No, that can be both. Whether or not it even does the pre-shuffle aggregation may not even be defined either, because that's an optimization, right? You can do the shuffle before doing the pre-aggregation, and then once you're sure that all of the values for the same key are on the same machine, you can do the aggregation after that. So that's an optimization. So technically speaking, for correctness, it doesn't even have to do the pre-shuffle aggregation at all. I'm going to stand here until somebody asks something. You can go if you're bored.
Can you come there to ask the question?
What?
Can you come here to ask the question? Because like office hours start.
Yeah, office hours is now.
First, I'll talk about this thing. I'm facing still some commission issue. I want to know, like, the project one is not credit yet for me.
Oh, can you grab Tosby?
Sorry,
Can you grab Tosby? Can you go get her?
who?
Tosby?
Wait, that's sweet.
Dylan, did you do something?
Yeah, I just wanted to know, should I meet you like here-ish on Friday or?
Oh, yeah, that's fine.
Thank you again. See you then.
Okay. I need to have a conversation with you both.
Yes.
I'll be back in a few minutes. Sounds like that.
You want to go? Oh, no. Because the ones coming back now, man.
It's okay, we'll have extended office hours.